Given 2 points on the plane and a path S joining them, the path differential ds can be expressed according to the hypotenuse of a triangle of sides differential of x and differential of y. Dividing on both sides by the differential of y and isolating the path differential, we find an expression that after integration gives the total length s of the path. Let us apply now to this same calculation the inner vision that was introduced in Chapter 1 of this video series called A Cyclical Universe. To apply the inner vision means to look at the same phenomenon, but now from within the structure. At that time, it was argued that this could be achieved by making the y-axis be a pure imaginary axis. On the other hand, since the y-axis corresponds to the axis of absence, and since absence was identified with time, this new perspective from inside the structure can be achieved by changing from y to iy and then expressing y as ct. However, let the order be reversed here. First we will change y to ct and then we will introduce the imaginary unit I. So let's first introduce the time variable. In this way, the length of the path is expressed in terms of a speed. Next, we move on to the inner vision itself by introducing the imaginary unit. Its main effect is to change the sign inside the square root to make it become the inverse of the Lorentz factor. Then, by applying the fact that the derivative of t with respect to tau is the Lorentz factor itself, this integral ends up becoming I times c delta tau. IC times delta tau is also an arc of circumference. That is, the fact that the relation dt over d tau equals gamma was applied also introduced a concrete relation between t and x, which is the relation of the circle since t is proportional to the sine and x to the cosine. Then, the principle of most proper time states that among all possible paths between the 2 points on the plane, the real trajectory is the one that maximizes delta tau, which implies, in this previous expression, minimizing the term b squared over c squared. However, if the negative sign changes to positive, such as in the first step performed above, then to minimize b squared over c squared also involves minimizing the value of the integral. Therefore, maximizing the proper time interval actually means, from an external point of view, finding the path with least length between the two given points on the plane, which is none other than a straight line. On the other hand, to travel from one point to another in a straight line at a given amount of time, a constant velocity will always make the term v squared be lower than a velocity that varies around its average value, since the square of an average value is always lower than the average of the squared value itself. The main conclusion to be drawn is that seen from the outside, the path with the most proper time corresponds to a uniform linear motion, which is nothing but Newton's first law, which states that inertial motion is a straight line at a constant speed. Therefore, the principle of most proper time is none other than an inner view of Newton's first law. Finally, we remark a result that will be useful to us later: the fact that the length of a path on the plane is equivalent to an interval of proper time.